Below is an end-toned overview of how modern semiconductor chips are conceived, designed, manufactured, packaged, integrated into products, and shipped, along with representative companies involved at each step in their stock tickers. Sequences often overlap in practice, but this captures the major phases and flows. 1. Product definition, planning, and architecture. What happens? Market analysis, product requirements, performance, power, area, cost, target nodes, make by IP strategy, schedule and risk plan, architecture definition, compute blocks, accelerators, memory hierarchy, interfaces, representative players, Fables ADM product owners, NVIDIA, NVDA, AMD, Qualcomm, QCOM, Apple AAPL, MediaTek, 2454 TW, Broadcom, AVGO, Marvell, MRVL, Tesla, TSLA, for in-house auto SoCs, NXP, NXPI, ST Microelectronics SDM, Infineon, IFXDE, ADR, IFNNY, Texas Instruments, TXN, Analog Devices ADI, Microchip MCHP, onsemi, on, Renesas, 6723T, Cloud Compute Planning Tools, Amazon AWS AMZN, Microsoft Azure MSFT, Google Cloud Google for EDA Compute and Collaboration. 2. IP strategy and acquisition. What happens? Selection licensing of CPU, GPU, DSP cores, interconnects, PHYs, DDR, LPDDR, C, SerDes, security blocks, and standard cell libraries IOs, representative IP and library vendors, ARM CPU, GPU, SOC IP ARM, Synopsys Designware IP, SNPS, Cadenced in Silica and Interface IP, CDNS, CEVA DSP IP CEVA, Rambus Memory SerDes IP, RMBS, Imagination GPU IP, private, NC5 RISC-V cores, private, Foundry PDKs and libraries, TSMC, TSM, Samsung Electronics, 005930KS, Global Foundries, GFS, UMC, Intel Foundry, INTC. 3. Front-end design RDL to gates. What happens? Microarchitecture, RDL coding, simulation, formal verification, power performance area analysis, synthesis, static timing, DFT insertion ScanBist, EDA tool vendors, Synopsys, SNPS, design compiler, VCs, PrimeTime, Fusion compiler, Cadence, CDNS, Genus, Celium, Jasper Gold, Inopus, Siemens EDA, CG, Questa, Calibre, also used in physical verification. 4. Physical design and sign-off. What happens? Floor planning, placement, routing, clock tree, IREM analysis, physical verification, DRC-LVS, parasitic extraction, eco-closure, TPIA package preparation, EDA and verification, Cadence, CDNS, Synopsys, SNPS, Siemens EDA, CG, ANSYS, ANSS, for power integrity thermal, Keysight, Keys, for high-speed channel and RF simulation. 5. TPIA in photo mask production. What happens? Final GDS OASIS data goes to mask shops. Reticles are written for each layer. Mask and mask blank providers. Photronics, Plab, Toppen, 7911T, Dynapon Printing DNP, 7912T, Hoya 7741T, for mask blanks. 6. Wafer fabrication, foundries and IDMs, what happens, feel, transistor formation, and BL, interconnect, across dozens to 1,000 steps, deposition, lithography, etch, clean, implant, CMP, metrology, inspection, anneal. Advanced nodes use UV, foundries, TSMC, TSM, Samsung Electronics, 005930KS, Intel Foundry, INTC, Global Foundries, GFS, UMC, SMIC, 0981HK, IDM Memory, IFDRAM NAND, Samsung, 005930KS, SK Hynix, 000660KS, Micron, Mu, Kioxia, Private, Western Digital for NAND JV, WDC, Core Equipment Suppliers, Lithography, ASML, Nikon, 7731T, Canon 7751T, Etch Deposition, Applied Materials AMAT, Lam Research, LRCX, Tokyo Electron, 8035T, ASM International, Azimuth, ADR, ASMIY, Metrology Inspection, CLA, CLAC, Onto Innovation Anta, Hitachi High-Tech, 8036T, Coder Developer and Cleans, Screen Holdings, 7735T, Ion Implant, Axelis, ACLS, Applied Materials AMAT, Thermal, Kokusai Electric, 6525T, TAL, 8035T, 7 Materials, Gases, and Consumables, Wafers, Shin-Etsu Chemical, 4063T, SUMCO, 3436T, Siltronic, WAF-DE, Gases, Linda, Lin, Air Liquide, AIPA, Air Products, APD, Photoresist Chemicals SLMs, JSR, 4185T, Tokyo Okokogyo Talk, 4186T, DuPont, DD, Merck KGaAMD Electronics, MRKDE, CMP Slurries Filters FOPS, Entegris, ENTG, Mask Blanks, Hoya 7741T, 8, Yield Engineering and Process Control, what happens, Inline Metrology, EBIM Optical Inspection, Statistical Process Control, Failure Analysis, Design for Manufacturability, Yield Learning, Masco PC Tweaks and Stepping Revisions, Key Vendors, CLA, CLAC, Onto Innovation Anta, Applied Materials AMAT, Zeiss, Private, for UV Optics, EDA for DFM, Synopsys, SNPS, Cadence, CDNS, Siemens EDA, CG. 9. Wafer Sort, Electrical Test on Wafer, what happens, Probe Cards Contact Die, Basic Functionality and Speed Bins Determined, Bad Dies Inked or Mapped, Test Vendors and Equipment, Teradyne, TER, Advantest, 6857T, 8, Form Factor, Form, Probe Cards, Kohu, SPI, Private, Handlers, 10, Assembly, Packaging, and Final Test, OSATs and IDMs, what happens, Singulation, Die Attach, Wire Bonding or Flip Chip, Underfill, Molding, Advanced Packaging, 2.5D/3D, Chiplets, FOWLP, fan-out, CoWoS-info, burn-in and final test, OSITs, outsourced assembly and test, ASE Technology NYSE, ASX, 3711 TW, Amcor, AMKR, JCET, 600,584 SS, Powered Etch, 6,239 TW, Chipland, 6,147 TW, Advanced Packaging Materials Substrates, Ajinomoto, 2,802 T, for ABF Films, Ibiden, 4,062 T, Chico Electric, 6,967 T, Animacron, 3,037 TW, Nanya PCB, 8,046 TW, Cooligan SofaClick, Bonders, Disco, 6,146 T, Dicing, Final Test, Teradyne, Ter, Advantest, 6,857 T, Kohu, 11, Logistics to chip customers, what happens, finished ICs are packed, labeled, and shipped to OEMs, ODMs or distributors, lot traceability and compliance stocks included, distributors, Arrow Electronics ARW, Avnet, AVT, WPG Holdings, 3,702 TW, Freight Logistics, DHL Group, DPDHLDE, FedEx FDX, UPS 12, Board Level Integration and System Manufacturing, what happens, chips placed on PCBs, power delivery, memory, RF subsystems, firmware bring up, EVT, DVT, PVT validation, regulatory certifications FCC CEUL, reliability, HALTAS AEC-Q 100 for auto, compliance, Rose Reach, EMS-ODM Partners, Foxconn Hanhai, 2,317 TW, Pegatron, 4,938 TW, Quanta, 2,382 TW, Compal, 2,324 TW, Wistron, 3,231 TW, Jabal, JBL, Flex, PCB ODM ecosystem also includes Lenovo, 0992HK, HP, HPQ, Dell, Compal, Quanta for notebooks and servers, 13 OEM product assembly and software enablement, what happens, system assembly, enclosure, thermal mechanical integration, OS driver enablement, security provisioning, calibration, factory test, packaging for retail B2B, representative OEMs, consumer PC, Apple AAPL, Samsung Electronics, 005930KS, HP, HPQ, Dell, Lenovo, 0992HK, Asus, 2357 TW, Acer 2353 TW, Sony, 6758 T, Mobile, Apple AAPL, Samsung, 005930KS, Xiaomi 1810HK, Oppo Vivo, Private, Data Center, Supermicrocomputer, SMCI, HPE, Dell, Inventec, 2356 TW, Automotive Tier 1S integrating chips into ECUs, Continental, Conde, Denso, 6902T, Aptiv, APTV, Magna MGA, 14, distribution of the finished consumer product, what happens, forecasting, channel allocation, retail online distribution, after-sales support, Field Returns Analytics, Retail Channel Logistics, Amazon, AMZN, Best Buy BBY, Apple Retail, AAPL, Carriers, VZT, TMUS, Regional Logistics Partners FDX, UPS, DPDHLDE. How these phases connect and iterate NPI program management threads through all steps, with risk reviews at architecture, RDL freeze, to PIOT, first silicon, and production milestones, feedback loops, silicon bring up and test result feedback to design, eco-steppings, and to process yield teams for continuous improvement. For advanced products, chiplet and advanced packaging choices are made early because substrate lead times and offset capacity are on the critical path. Special cases and variations ADMs handle many steps in-house, TI, ADI, Infineon, ST Micro, onsemi, though they may still use foundry offset selectively. Memory supply chains operate similarly but with memory-specific tooling, test, and packaging flows. Samsung, SK Hynix, Micron, Automotive as extended qualification, AECQ, IATF 16949, and PPAP documentation across the supply chain. Typical critical path lead times, designed to PIT, 6-24 plus months depending on complexity. Mask build, 1-3 weeks, can be longer for complex UL sets. Below is an end-to-end view of how chips go from concept to consumer products, with representative companies commonly involved at each phase in their stock tickers. Not every program uses every firm. These are typical examples for each step. 1. Product definition, planning, and architecture, activities, market sizing, competitive analysis, performance power area cost targets, PPAC, node selection, make-buy for IP, program schedule, risk and supply planning, SOC system architecture. Typical product owners, Fables ADMs, NVIDIA, NVDA, AMD, Qualcomm, QCOM, Apple AAPL, MediaTek, 2454 TW, Broadcom, AVGO, Marvell, MRVL, NXP, NXPI, ST Microelectronics SDM, Infineon, IFXDE, ADR, IFNNY, Texas Instruments, TXN, Analog Devices ADI, Microchip MCHP, onsemi, Renesas, 6723T, Cloud Compute Frida Collaboration, Amazon AWS AMZN, Microsoft Azure MSFT, Google Cloud Google. 2. IP strategy and acquisition, activities, license select CPU GPU DSP cores, SIRTA CDDR LPDDR USB PHYs, security, interconnects, standard cells IOs, align with foundry PDKs, IP library vendors, ARM, Synopsys Designware, SNPS, Cadenced in Silica Interface IP, CDNS, CEVA, Rambus RMBS, Foundries providing PDKs libraries, TSMC, TSM, Samsung Electronics, 005930KS, Intel Foundry via Intel, INTC, Global Foundries, GFS, UMC, SMIC, 0981HK. 3. Front-end design RDL to gates, activities, microarchitecture, RDL coding, simulation, formal verification, power performance analysis, synthesis, DFT ScanBest, static timing, lint CDC, key EDA providers, Synopsys, SNPS, Cadence, CDNS, Siemens EDA via Siemens AG80R, CG, etc., ZDE. 4. Physical implementation and sign-off, activities, floor plan, place route, clock tree, IREM thermal, parasitic extraction, STA sign-off, physical verification, DRC-LVS, eco-closure, tape-out package collateral, tools and analysis, Cadence, CDNS, Synopsys, SNPS, Siemens EDA, CG, ANSYS for power thermal, ANSS, Keysight for high-speed RF, keys. 5. Photomask preparation and manufacturing, activities, final GDS OASIS, OPC RET, mask writing, pellicles and inspection, mask shops blanks, photronics, PLAB, Toppen, 7911T, Dynapon printing DNP, 7912T, Hoya 7741T. 6. Wafer fabrication, field beal, activities, hundreds to 1000 steps across deposition, lithography, WV, etch, clean, implant, CMP, anneal, metrology, inspection, multi-patterning, copper low-K interconnect stacks, scribe and sort prep, pure play foundries and IDMs, TSMC, TSM, Samsung Electronics, 005930KS, Intel Foundry via Intel, INTC, Global Foundries, GFS, UMC, SMIC, 0981HK, Memory IDMs, for DRAM NAND, Samsung, 005930KS, SK Hynix, 000660KS, Micron, Mu, Western Digital WDC, NANJV, Core Equipment Suppliers, Lithography, ASML, Nikon, 7731T, Canon 7751T, HDEP CVD ALD, Applied Materials AMAT, Lam Research, LRCX, Tokyo Electron, 8035T, ASM International, ASMS, ADR, ASMIY, Metrology Inspection, CLA, CLAC, Anta Innovation Anta, Hitachi High-Tech, 8036T, Coders Developers Clean, Screen Holdings, 7735T, Ion Implant, Axelis, ACLS, Applied Materials AMAT, Thermal, Kokusai Electric, 6525T, Tokyo Electron, 8035T, 7 Materials, Gases, and Consumables, Silicon Wafers, Shinetsu Chemical, 4063T, SUMCO, 3436T, Siltronic, WAF-DE, Specialty Gases, Linda, Lin, Air Liquide, AIPA, Air Products, APD, Photoresist Chemicals, JSR, 4185T, Tokyo Okakoji Otak, 4186T, DuPont, DD, Merck KGaAMD Electronics, MRKDE, CMP Slurries Filtration FOPS, Entegris, ENTG, Mask Blanks Pellicles, Hoya 7741T. 8. Yield Engineering and Process Control, Activities, Inline AP Overlay Metrology, Defect Inspection, SPC, Tool Matching, Process Window Optimization, Failure Analysis and FIB, DFMOPC Updates, Stepping Ecos, Vendors and Tools, CLA, CLAC, Anta Innovation Anta, Applied Materials AMAT, ETA DFM from Synopsys, SNPS, Cadence, CDNS, Siemens ETA, CG. 9. Wafer Sort, Probe Test at Wafer, Activities, Electrical Probe, Functional Tests, Speed Power Binning, Bad Die Mapping, Test Ecosystem, Teradyne, TER, Advantest, 6857T, 48, Form Factor, Form, Probe Cards, Kohu, Handlers, 10, Assembly, Packaging, and Final Test, OSATs IDMs, Activities, Wafer Dicing, Die Attach, Wire Bond or Flip Chip, Underfill, Molding, Substrate Attach, Advanced Packaging, 2.5D/3D, Chiplets, Fan-Out, FOWLP, Info-CoWoS, Burn-In and Final Test, OSATs, ASE Technology, ASX, 3711 TW, AMCOR, AMKR, JCET, 600,584 SS, Powered Etch, 6,239 TW, Chipment, 6,147 TW, Advanced Substrates Materials and Tools, Ajinomoto ABF, 2,802T, Iboden, 4,062T, Chico Electric, 6,967T, Animicron, 3,037 TW, Nanya PCB, 8,046 TW, Kulik and Sofa Bonders, Click, Disco Dicing, 6,146 T, Final Test, Teradyne, TER, Advantest, 6,857 T, Kohu, 11, Logistics to Chip Customers, Activities, Lot Traceability, Moisture Sensitivity Handling, Labeling Packing, Compliance Docs, Rose Reach, Shipment to OEMs ODMs or Distributors, Arrow Electronics ARW, Avnet, AVT, WPG Holdings, 3,702 TW, Freight Logistics, DHL Group, DPDHLDE, FedEx FDX, UPS, 12, Board Level Integration and System Manufacturing, Activities, PCB Design and Assembly, Power Delivery, Memory and RF Integration, Firmware Boot Bring Up, EVT DVT PVT Validation, Regulatory, FCC CEUL, Reliability, Holt-Haas, AEC Q100 Ferrato, EMS ODM Partners, Foxconn Honhai, 2,317 TW, Pegatron, 4,938 TW, Quanta, 2,382 TW, Compal, 2,324 TW, Wistron, 3,231 TW, Jabal, JBL, Flex, 13 OEM Product Assembly and Software Enablement, Activities, System Assembly and Thermal Mechanical Integration, OS Driver Enablement, Security Provisioning, Calibration, Factory Test, Packaging for Retail B2B, Representative OEMs, Consumer PC, Apple AAPL, Samsung Electronics, 005930KS, HP, HPQ, Dell, Lenovo, 0992HK, Asus, 2357 TW, Acer 2353 TW, Sony, 6750 AT, Data Center Systems, Supermicro Computer, SMCI, Hewlett-Packard Enterprise, HPE, Dell, Automotive Tier 1S integrating chips into ECUs, Continental, Conde, Denso, 6902T, Aptiv, APTV, Magna MGA. 14. Distribution of the finished consumer product, activities, demand planning, channel allocation, regional compliance labels, retail online distribution, carrier partnerships, mobile, after-sales support, field returns analysis, retail carriers logistics, Amazon, AMZN, Best Buy BBY, Apple Retail APL, Verizon VZ, AT&T, T-Mobile, TMUS, DHL, DPDHLDE, FedEx FDX, UPS. Timing and feedback loops, typical critical path, 6-24 plus months from concept to tape out, 1-3 plus weeks for mask build, 8-16 plus weeks for fab cycle at advanced nodes, packaging test 2-6 weeks, system integration validation varies by product, feedback, silicon bring up and test data drive eco steppings, yield learning updates design rules OPC, field data informs next, gen product definition, variations ADMZG, TXN, ADI, STM, IFX, on, may handle design, fab, and packaging in-house, using external foundry OSAT selectively. Memory supply chains follow similar steps with memory-specific tooling and test flows. Samsung, SK Hynix, Micron, advanced chiplet/3D packaging requires early substrate and OSAT capacity planning due to long lead times. Below is a comprehensive, end-to-end overview of how modern semiconductor chips go from idea to consumer products. It follows the life cycle from initial planning to system integration and retail distribution, and for each stage it cites representative companies commonly involved and their stock tickers. Not every program uses every firm, and many activities are done in parallel, but this framework reflects mainstream industry practice. 1. Market discovery, product definition, and program planning. What happens? The journey begins with market research and requirements capture. Teams size the opportunity, study competitors, define performance power area cost, PPAC, targets, budget, and schedule. They choose a process node e.g. N5/N3 at TSMC, Intel 18A, based on economics and technical needs, decide which functions to integrate CPUs, GPUs, AI accelerators, connectivity, security, and identify supply risks and partners, foundry, OSAT, substrate, materials representative product owners, fables ADM, NVIDIA, NVDA, AMD, Qualcomm, QCOM, Apple APL, MediaTek, 2454 TW, Broadcom, AVGO, Marvell, MRVL, NXP, NXPI, ST Microelectronics STM, Infineon, IFXDE, ADR, IFNNY, Texas Instruments, TXN, Analog Devices ADI, Microchip MCHP, Onsemi, Renesas, 6723T, Program Infrastructure, Cloud Compute Frida Collaboration and Regression Farms is often hosted on Amazon Web Services, AMZN, Microsoft Azure MSFT, or Google Cloud. Google Outcome, a product requirements document, program plan, budget, and a high-level architecture. 2. IP strategy, ecosystem alignment, and licensing. What happens? Teams decide what to build versus buy. Buying mature IP e.g. CPU cores, SerDes PHYs, DDR LPDDR controllers, Security accelerators, reduces risk time to market. The design must align with Foundry PDKs, process design kits, and libraries, key IP library vendors, ARM CPU GPU SoC IP ARM, Synopsys Designware IP, SNPS, Cadenced in Silica and Interface IP, CDNS, CEVA DSP IP CEVA, Rambus Memory and CERDES IP, RMBS, Foundries providing PDKs and foundation libraries, TSMC, TSM, Samsung Electronics, 005930KS, Intel Foundry via Intel, INTC, Global Foundries, GFS, UMC, SMIC, 0981HK, Outcome, Licensed IP Portfolio, NDA PDK access, and a verified integration plan. 3. Microarchitecture and front-end design RDL to gates. What happens? Architects translate requirements into microarchitecture specs. Design engineers code RDL Verilog VHDL system Verilog, run unit and system simulations, formal verification, and power performance modeling. DFT design for test, features like scangains and built-in self-test, BIST, are inserted. Synthesis converts RDL into gate-level netlists, followed by timing and power closure cycles, EDA leaders, Synopsys, SNPS, VCs, Design Compiler, Fusion Compiler, PrimeTime, Cadence, CDNS, Celium, Jasper Gold, Genus, Joules, Siemens EDA, part of Siemens AG ADR, CG, etc., ZDE, Questa, Verification IP, Outcome, Functionally Verified RDL, Synthesized Netlists, Test Strategy, and Constraints for Physical Design. 4. Physical Implementation and Sign-Off. What happens? Physical design transforms netlists into manufacturable layouts. Steps include floor planning, partitioning, place and route, clock tree synthesis, IR drop and electromigration analysis, parasitic extraction, static timing analysis, STA, and physical verification, DRC-LVS. Designers also develop package floor plans early to coordinate bump maps, power delivery, and thermal design. Tools and analysis providers, Cadence, CDNS, Inopus, Voltus, Tempus, Synopsys, SNPS, ICC2/Fusion, PrimeTime SA, Star RC, Siemens EDA, CG, Caliber, DRC-LVS, M-Power, ANSYS, ANSS, Red Hawk SC, SIWAV, Thermal CFD, Keysight, Keys, High-Speed Channel RF Cool Simulation, Outcome, Sign-Off Clean Layout Data, GDS Oasis, Package Collateral, Test Vectors, and Documentation for Tape-Out. 5. Tape-Out Data Prep, OPC RET, and Photo Mask Production. What happens? Tape-Out bundles final design data for the foundry and mask shop. Resolution enhancement techniques, RET, and optical proximity correction, OPC, modify patterns to print correctly at nanometer scales. Mask data is fractured and written to reticles. UV-Dub masks are inspected and, for DUV, protected by pellicles, mask and mask link providers, Photronics, PLAB, Mask Writing Services, Toppen Holdings, 7911T, Photomasks, Dynapon Printing, DNP, 7912T, Photomasks, Hoya, 7741T, Mask Blanks and Pellicles, Outcome, a full mask set delivered to the foundry, often 50-100 plus reticles for advanced SoCs. 6. Wafer fabrication in the foundry, Feel and Beal. What happens? The foundry turns bare silicon wafers into patterned devices across hundreds to more than 1,000 process steps. Front end of line, Feel, builds transistors with ion implantation, gate stack formation, and epitaxy. Back end of line, Beal, creates interconnect layers with deposition, lithography, etch, and chemical mechanical planarization (CMP). Advanced nodes use UV lithography to reduce multi-patterning. Strict process control ensures line width, overlay, and effectivity stay within spec. Pure play foundries and IDMs, TSMC, TSM, Samsung Electronics, 005930KS, Intel Foundry via Intel, INTC, Global Foundries, GFS, UMC, SMIC, 0981HK. Memory IDMs, for DRAM NAND flows, Samsung, 005930KS, SK Hynix, 000660KS, Micron, Mu, Western Digital for NAND JV, WDC, core equipment suppliers, lithography, ASML, Nikon, 7731T, Canon 7751T, etch deposition CVD Applied Materials AMAT, Lam Research, LRCX, Tokyo Electron, 8035T, ASM International, Azumas, ADR, ASMIY, Metrology Inspection, CLA, CLAC, Anta Innovation Anta, Nova, NVMI, Camtaxi AMT, Coders Developers Clean, Screen Holdings, 7735T, Ion Implant, Axelis, ACLS, Applied Materials AMAT, Thermal Processing, Kokusai Electric, 6525T, Tokyo Electron, 8035T, Facilities and Yield Infrastructure, Inline Metrology, Defect Inspection, Advanced Process Control APC, and Statistical Process Control, SPC, run continuously to tune recipes and improve yields. Outcome, finished wafers containing many copies of the chip, dies, with electrical parametrics within target distributions. 7 materials, gases, and consumables supporting the fab. What happens? The fab relies on ultra-pure materials and consumables, prime silicon wafers, specialty gases, argon, nitrogen, hydrogen, fluorine chemistries, photoresist, developers, CMP slurries, filters, and advanced packaging precursor materials. Key suppliers, silicon wafers, Shinetsu Chemical, 4063T, SUMCO, 3436T, Siltronic, WAF-DE, Specialty Gases and Abatement, Linda, Lin, Air Liquide, AIPA, Air Products and Chemicals, APD, Photoresists and Chemicals, JSR, 4185T, Tokyo Okokogyo Talk, 4186T, DuPont, DD, Merck KGaAMD Electronics, MRKDE, Contamination Control, CMP, FOPS, Entegris, ENTG, Mask Blanks and Pellicles, Hoya 7741T, Outcome, stable supply of critical materials with tight quality controls and traceability. 8. Yield engineering, process control, and design for manufacturability, DFM. What happens? Yield engineers correlate inline data, failure analysis, FA, and wafer sort results to find systematic defects, tune OPC, and update design rules, E-beam and optical tools inspect critical layers, FIB, focused ion beam edits can help diagnose defects. DFM feedback loops might trigger minor design echos or mask revisions, steppings, to recover yield or improve performance. Representative vendors tools, metrology inspection and yield, CLA, CLAC, ONTA Innovation ONTA, NOVA, NVMI, Applied Materials AMAT, DFM sign-off and pattern matching, Synopsys, SNPS, Cadence, CDNS, Siemens EDA, CG, Outcome, yield ramps from low initial values to production targets, often 80-95% plus depending on complexity and maturity. 9. Wafer sort, electrical probe and binning. What happens before dicing? Automated test equipment. 8. Probes each die to screen out non-functional parts and to bin by speed power. Probe cards must make reliable contact with microscopic pads or micro bumps. Bad dies are mapped so only known good die proceed to assembly, especially crucial for multi-die chiplet packages. Key ecosystem, 8 vendors, Teradyne, TER, Advantest, 6857T, probe cards, form factor, form, handlers, Kohu, outcome, known good die, KGD, maps and speed power bins that drive package and product SKUs. 10. Assembly, packaging, and final electrical test. What happens? Wafers are diced, and dies are assembled into packages. Conventional packaging involves die attach, wire bonding or flip chip, underfill, mold, and marking. Advanced packaging enables higher bandwidth and heterogeneous integration. 2.5D interposers, fan-out wafer-level packaging, FOWLP, chiplets on organic or glass substrates, and 3D stacking with through-silicon vias, TSVs. Final test and burn and screen out early life failures and verify functionality across temperature offsets. Outsourced assembly and test, ASE Technology NYSE, ASX, 3711 TW, Amkor, AMKR, JCET, 600,584 SS, Powered Etch Technology, 6239 TW, Chipland, 6147 TW, additional substrate packaging ecosystem, Tongfu Microelectronics, 002156SZ, Kayak, 2449 TW, for test, substrate and materials providers for advanced packaging, Ajinomoto Fine Chemicals ABF Films, 2802T, Ibiden, 4062T, Shiko Electric Industries, 6967T, Animacron, 3037 TW, Nanya PCB, 8046 TW, Adines, ATS, 6, Equipment Vendors, Kulik and Sofa Bonders, Click, Disco Dicing Saws, 6146 T, Final Test Partners, Teradyne, TER, Advantest, 6857 T, Kohu, Outcome, Packaged ICS, Tested and Bend, with Traceability and Moisture Sensitivity Labeling MSL. 11. Logistics and distribution of chips to OEMs ODMs. What happens? Finished ICS are dry packed with desiccants and humidity indicators, labeled with lot date codes, and shipped to customers or distributors. Quality documentation, PPAP for auto, certificates of conformance, RoHS REACH compliance, and reliability data accompany shipments. For sensitive parts, cold chain or ESD-controlled handling is used. Distributors: Arrow Electronics ARW, Avnet, AVT, WPG Holdings, 3702 TW, Freight Logistics Providers, DHL Group, DPDHLDE, FedEx FDX, UPS Outcome. Chips arrive at board manufacturers and OEMs with full traceability. 12. Board-level integration, firmware, and system validation. What happens? OEMs or MSODM partners place chips on PCBs alongside power management, memory, RF front ends, sensors, and connectors. They develop boot firmware, drivers, and low-level software, then run bring-up and characterization. Engineering validation test, EVT, design validation test, DVT, and production validation test, PVT. Cycles measure functionality, performance, signal integrity, EMC, and reliability. Products undergo regulatory certification, FCC-CEUL, environmental and reliability testing, HAS, and, for automotive, AEC, Q100 qualifications at chip level and ISO 26262 functional safety at system level, MSODMs, Foxconn Hon-Hai, 2317 TW, Pegatron, 4938 TW, Quanta, 2382 TW, Compal, 2324 TW, Wistron, 3231 TW, Jabil, JBL, Flex, Test and Measurement Partners, Keysight, Keys, and Ritsu, 6754 T, Roden Schwartz, Private, for RFEME, National Instruments Now NI, part of Emerson Electric EMR Outcome, validated boards and systems ready for mass production, with production test limits and golden images frozen. 13. OEM product assembly, software enablement, and factory test. What happens? The final product is assembled, integrating electronics, mechanicals, and thermal solutions. Manufacturing lines load firmware OS, calibrate sensors and radios, provision security keys, and execute end-of-line tests. Packaging for retail or enterprise channels is finalized. Data from factory tests feeds into yield dashboards and continuous improvement for both system and silicon, e.g., if a corner case issue traces back to a silicon erratum, an eco or stepping may be scheduled. Representative OEMs, Consumer Electronics PC, Apple AAPL, Samsung Electronics, 005930KS, HP, HPQ, Dell, Lenovo, 0992HK, Asus, 2357 TW, Acer 2353 TW, Sony, 6758 T, Mobile, Apple AAPL, Samsung, 005930KS, Xiaomi 1810HK, plus Oppo and Vivo. Private, Data Center Systems, Supermicro SMCI, Hewlett-Packard Enterprise, HPE, Dell, Automotive Tier 1S integrating chips into ECUs, Continental, ConDE, Denso, 6902T, Aptiv, APTV, Magna MGA Outcome. Finished goods approved for volume production, with stable yields and costed bills of materials ROMs. 14. Distribution of finished consumer products and after-sales feedback. What happens? OEMs plan demand, allocate channel inventory, coordinate regional SKUs and regulatory labeling, and launch marketing. Logistics ships to retail and enterprise channels. Carriers handle mobile device activations. After-sales service and field returns provide critical feedback for future revisions. Retail and channel, Amazon, AMZN, Best Buy BBY, Apple Retail APL, Carriers, Verizon VZ, AT&T T-Mobile TMUS, Global Logistics, DHL, DPDHLDE, FedEx FDX, UPS Outcome, products reach end users, field data loops back into roadmaps and quality systems. Inside the fab, deep dive into critical steps. Lithography, arguably the heartbeat of Moore's Law. Lithography uses scanners to project patterns on photoresist. U from ASML. ASML, with high NA variance, enables sub-30 nm pitch features with fewer masks than multi-patterned DUV pellicles and mask lengths from Hoya 7741T, and precision optics from Zeiss. Private, are key. Below is a deep, practical elaboration of the product definition, planning, and architecture phase in semiconductor development, how leading chip companies translate market opportunities into actionable programs. It covers the strategic and technical decisions made before any silicon is manufactured, including market sizing, competitive analysis, performance power area cost, PPAC, target setting, process node selection, make versus buy for IP, program scheduling and governance, risk and supply planning, and the SOC system architecture decisions that anchor the rest of the life cycle. Representative companies and tickers are referenced where relevant to illustrate industry practice. 1. Market discovery and sizing, TAM, SAM, SUM, and product positioning objective. Identify a compelling market need and quantify its size and growth through total addressable market, TAM, serviceable available market, SAM, and serviceable obtainable market, SUM. Define the value proposition, target customers, price envelope, and required differentiation activities, customer and use case research, engage OEMs, ODMs, hyperscalers, automotive Tier 1s, and industrial integrators to capture unmet needs and emerging standards. Companies doing this at scale include NVIDIA, NVDA, AMD, Qualcomm, QCOM, Apple APL, MediaTek, 2454 TW, Broadcom, AVGO, Marvell, MRVL, NXP, NXPI, ST Microelectronics STM, Infineon, IFXDE, ADR, IFNNY, Texas Instruments, TXN, Analog Devices ADI, Microchip MCHP, Onsemi, Renesas, 6723T, Market Modeling, Segment by End Market, Mobile, PC, Data Center, Automotive, Industrial IoT, Networking, Geography, and Price Tier. For AI and Data Center, factor in workload trends, MLPerf benchmarks, and total cost of ownership, TCO, drivers, power, space, cooling, revenue ASP strategy, define entry, mainstream, and flagship SKUs, each with a target ASP, margin, and features. Include speed, power bins and memory configurations, competitive positioning, identify key competitors and incumbents by segment, analyze their roadmaps, die sizes, nodes, software ecosystems, and supply strategies. 2. Competitive analysis and differentiation objective, map existing and anticipated competitor offerings and choose a unique path. This requires correlating architecture choices with tangible customer benefits, activities, feature performance mapping, compare compute density, bandwidth, latency, power efficiency, security features, safety certifications e.g. ISO 26262 for automotive, and software stack maturity, cost and supply comparisons, estimate competitor die sizes, package costs, and foundry relationships with TSMC, TSM, Samsung Electronics, 005930KS, Intel Foundry, INTC, Global Foundries, GFS, UMC. Consider substrate constraints e.g. ABF capacity from Ajinomoto, 2802T, and OSAT capacity at ASE Technology, ASX, 3711TW, and Amkor, AMKR, Ecosystem and Lock-in, Assess Developer Ecosystems CUDA, ROC, OS and driver support, toolchains, and certification status. These are often as critical as raw performance. 3. PPAC target setting and product requirements. Objective: translate market needs into quantifiable technical targets across performance, power, area, and cost. These become the North Star for architecture and project control activities. Performance targets: define throughput latency for critical kernels and benchmarks, set cache and memory bandwidth requirements, I/O targets, CXL, Ethernet, and acceleration needs AI, video, crypto, power and thermals. Establish power budgets at typical and worst-case workloads. Define thermal design power, TDP, junction temperature limits, and cooling solutions, air, liquid, vapor chamber, area and yield. Estimate die area based on block level sizing. Model yield using historical defect density at candidate nodes, TSMC N5/N4/N3, Samsung 4/3 nanometers, Intel 20A/18A. Smaller dies generally yield better. Chiplet strategies may be favored for very large designs. Cost model: build a bottoms-up model including mask set cost, wafer cost by node, expected yield, test assembly costs at OSATs ASE, Amkor, JCET 600584 SS, substrate costs, Ibudin 4062T, Shiko Electric 6967T, Animacron 3037 TW, add-in SATs, 6, logistics, and warranty reserves. Set gross margin targets aligned with corporate goals, quality and reliability. Define fit rates, burn-in requirements, and standards compliance. JEDEC, PCI-SIG, USPIF, IEEE, etc. For automotive, AEC Q100 grade targets, PPAP documentation, and functional safety goals. 4. Node selection and foundry engagement. Objective: pick the fabrication node and foundry partner that best meet PPAC, schedule, and risk constraints considerations. Technical capability in PPA, advanced nodes e.g. TSMC N3E N3P, Samsung SF3, Intel 18A, promise better performance and power but carry higher wafer and mass costs, yield complexity, and yield learning time. Mature nodes e.g. TSMC N7/N6/N16, Global Foundries December 22, 2028 nanometers, UMC 28/40 nanometers, offer lower risk and cost for analog, RF, power, and embedded applications. Capacity and cycle time, access to wafer starts, priority at high-demand nodes, and fab cycle times are critical. Early engagement with TSMC, TSM, Samsung, 005930KS, Intel Foundry, INTC, Global Foundries, GFS, and UMC secures slots and influences DFM rules, ecosystem fit, availability of PDKs, foundation libraries, memory compilers, and PHY IP portfolios, multi-source options if supply resilience is required, packaging co-development, advanced packaging options e.g., TSMC CoWoS InfoSotic, must be aligned early. OSAT partners like ASE ASX, Amkor, AMKR, and substrate suppliers, Ajinomoto 2802T, Ibudin 4062T, shape the feasibility of 2.5D/3D in chiplet architectures, geopolitical and compliance, export controls, country of origin rules, and customer procurement constraints may influence foundry selection, outputs, node choice, preliminary wafer pricing, mask lead times, NRE budget, risk register, and a joint technology engagement plan with the foundry. 5. Make versus buy IP strategy. Objective: accelerate time to market and reduce risk by licensing IP blocks where differentiation is low, and building in-house where differentiation is high, by candidates, CPU, GPU, DSP and subsystem IP, ARM, ARM for CPU, GPU, cadenced in silica, CDNS, and CEVA for DSPs, interface and memory IP, Synopsys Designware, SNPS, Cadence, CDNS, Rambus RMBS, for DDR LPDDR, CCXL, CIRDES, and security, standard cells, iOS, SRAM compilers, provided with foundry PDKs from TSMC, Samsung, Intel Foundry, Global Foundries, UMC, SMIC, 0981HK, build candidates, differentiating accelerators AI, imaging, signal processing, interconnect fabric customization, power management, and security root of trust, evaluation, maturity and silicon history, PPA claims versus silicon data, configurability, verification collateral, testability, and licensing models, upfront versus royalty, outputs, licensed IP portfolio, work breakdown structure, WBS, for internal blocks, and integration plan with versioning and change control. 6. System and SoC architecture, objective, define the partitioning of functions across DICE chiplets and system components, lock the interfaces and performance model to meet PPAC and schedule goals, key decisions, monolithic versus chiplets. Chiplets reduce reticle limited die size and can mix nodes e.g., logic at N3, I/O at N6, SRAM cache die on mature nodes, but add packaging cost and interconnect latency. Packaging choices include 2.5D interposers, organic substrates with high-density redistribution, and 3D stacking with TSVs, compute and memory hierarchy, choose core counts and types, ARM, RISC-V, custom, cache sizes and policies. HBM versus DDR5/LPDDR5, X, memory, on-die scratch pads for accelerators, and coherency domain definitions, on-chip network, select or design network on-chip, NoC, with bandwidth latency tiers, costs, security isolation, and traffic shaping. External I/O, determine CCXL lanes, Ethernet SerDes speeds, USB display, MIPI, and high-speed PHY placement relative to power and thermal constraints, power delivery and management, multi-rail architecture, DVFS states, clock power gating strategy, always-on domains, and low-power islands for mobile IoT, security, hardware root of trust, secure boot, crypto accelerators, key storage, side channel resistance, and security update mechanisms, safety and reliability. For automotive industrial, adopt lockstep cores, ECC everywhere, diagnostics, watchdogs, and safety islands, support SEAL targets and collect safety metrics, co-design, package co-design, early bump map, PDN, thermal, and mechanical constraints, simulate hotspot mitigation and airflow with ANSYS, ANSS, and Keysight, keys, tools, board and system fit, for OEM constraints smartphones, laptops, servers, align with form factor, Z-height, connector placement, and cooling solutions. 7. Software and workload first planning, objective, ensure that hardware investments translate into real-world performance and developer adoption, activities, workload modeling, create cycle-accurate or trace-driven models, emulate with FPGA prototypes or hybrid virtual platforms, use cloud compute on Amazon AWS AMZN, Microsoft Azure MSFT, Google Cloud Google to run large regression farms, compiler and driver strategy, plan toolchains, LLVM-GCC, proprietary compilers, kernel libraries, BLAS, DNNOps, and driver stacks across OS targets, Linux, Windows, Android, RTOS, middleware ecosystem. For AI, align with PyTorch TensorFlow graphs, ONNX, and inference compilers. For connectivity, ensure compliance with relevant consortium test suites, KPI definition, throughput watt, latency at costs, time to solution, and developer productivity metrics. 8. Financial modeling and business case, objective, validate that the program meets corporate ROI, margin, and cash flow goals under realistic scenarios. Components, NRE budget, EDA licensing, Synopsys SNPS, Cadence CDNS, Siemens EDA-CG, IP licenses, ARM-ARM, Synopsys SNPS, Cadence CDNS, Rambus RMBS, mask sets, bring up boards, validation equipment, and lab capital, COGS model, wafer cost, test assembly with OSIX ASE ASX, Amcor AMKR, JCET 600,584 SS, substrate cost and lead times, Ajinomoto 2802T, Ibudin 4062T, Animacron 3037 TW, Shiko 6967T, Logistics, DHLD PDHLDE, FedEx FDX, UPS UPS, Pricing and Volume, ASP by SKU, Ramp Curve, Distributor Margins, Arrow ARW, Avnet AVT, WPG 3702 TW, and rebates, sensitivity analysis, yield, mask respins, substrate shortages, macro demand shocks, and competitor pricing actions, output, go-no-go decision with stage-gated funding, targets encoded into OKR's KPIs. 9. Program structure, milestones, and governance. Objective, organize teams and set stage gates that manage risk and align cross-functional work, elements, organization, product management, system architects, RDL and physical design, verification, software, DFT-DFM, packaging, operations, supply chain, quality, and compliance, stage gates, PRD freeze, architecture review, RDL freeze, netlist freeze, tape-out readiness, first silicon, EVT, DVT, PVT, production release, schedules and buffers, build integrated schedules with critical path analysis, account for mask lead times from Photronics, PLAB, Toppen, 7911T, DNP, 7912T, and UV availability, tools and collaboration, issue tracking, requirements management, and CI/CD for design regressions hosted on Oz Azure GCP, secure VDI and EDA licensed servers, data governance for PDK and IP, reviews and metrics, weekly program syncs, executive reviews at gates, and dashboards for PPA progress, test coverage, defect burndown, and supply readiness. 10. Risk management and supply planning. Objective: anticipate and mitigate risks across technology, schedule, supply chain, and compliance. Risks and mitigations. Technology risk: new nodes or aggressive frequency targets may slip. Mitigate with de-risk vehicles, test chips, conservative voltage frequency assumptions early, and close foundry collaboration. TSMC, Samsung, Intel Foundry. Schedule risk: mask or EDA delays, IP late delivery, or verification bottlenecks. Mitigate with parallelization, extra compute on cloud, and feature prioritization for tape-out. Supply risk: ABF substrate constraints. Ajinomoto, limited offset capacity. ASE, Amkor, or wafer allocation. Mitigate with early capacity reservations, multi-sourcing, and die size optimizations. Geopolitical export controls, restrictions on advanced nodes or AI accelerators. Engage Trade Council, plan region-specific SKUs and performance caps if required. Quality and recalls, prevent with robust TFT-DFM, burn-in planning, and conservative D rates for early lots. Secure RMA processes with distributors, ARW, AVT, and OEMs output. A living risk register with owners, triggers, and response plans. Supply S&OP plan covering wafers to finished goods. 11. Packaging and test strategy during planning. Objective: lock the packaging roadmap consistent with performance, thermal, and cost goals. Ensure testability from day one. Considerations: conventional versus advanced packaging. Evaluate wire bond QFN, flip chip BGA, fan-out wafer-level packaging, FOWLP, 2.5D interposers, 3D stacking. Advanced options require long lead substrates and offset process readiness, substrate technology and vendors. ABF capacity and layer counts from Ibiden, 4062T, Shinko, 6967T, Animacron, 3037TW, Nanya PCB, 8046TW, Adines, ATS, 6. Thermal mechanical, heatsink interfaces, lid materials, underfill, and warpage control. Simulate with ANSYS, ANSS, test flow, define wafer sort coverage, KGD requirements for chiplets, burn-in, static dynamic, and final test at Teradyne, TER. Advantest, 6857T, Kohu, DFT hooks, scan, BIST, boundary scan, MBIST, must be designed in now. Output: a packaging DFM guide, BOM, preliminary test times costs, and also statements of work. 12. Standards, certification, and compliance planning. Objective: preempt obstacles related to interoperability and regulatory compliance activities. Interface compliance, plan for PCI-SIG compliance, CCXL, JEDEC memory standards, OSPF, VISA, MIPI Alliance, and Ethernet IEEE 800 2.3 test suites. Regulatory: EMC, EMI, FCC, CE, Safety UL, Environmental, RoHS REACH, and for automotive, IATF 16949 processes and ISO 26262 safety cases. Security and privacy, Secure Boot, FIPS 1403 crypto modules, and infield update strategies. Ensure hardware roots of trust and attestation strategies. Output: compliance matrix integrated into verification and validation plans. 13. Early physical feasibility and cost down levers. Objective: validate that the envisioned architecture is physically realizable. Chip manufacturing, from planning to shipping. 2,000 words. Below is a single, end-to-end narrative that follows a modern semiconductor product from the first market sizing meeting to the moment a finished consumer device reaches the end user. Each major phase is described, the key technical decisions that must be made, and the companies, with their publicly traded stock symbols, that typically participate. The flow is deliberately linear, but in practice many activities run in parallel and feed back into earlier stages. 1. Market discovery, product definition and program planning. What happens? Product owner teams, usually fabless design houses or integrated device manufacturers, begin with market research. They estimate total addressable market, TAM, serviceable available market, SAM, and serviceable obtainable market, SOM, for a new class of device, e.g., a 5nm AI accelerator for data center GPUs, a low-power 6nm SoC for flagship smartphones, or a 28nm microcontroller for automotive ECUs. Competitive analysis compares existing silicon, die size, node, power, price, and identifies gaps that a new product could fill. Key decisions: performance, power, area, cost, PPAC, targets, e.g., 2 TFLO PSW, 10 mm to the power of 2 die, 30 DLRBMs, process node selection, advanced nodes, TSMC N3/N4, Samsung 4nm, Intel 18A, for high-performance parts, mature nodes. Global Foundries 12nm, UMC 28nm, for cost-sensitive or analog designs. McAfee IP decide which blocks will be built in-house, e.g., custom AI accelerator, and which will be licensed, e.g., ARM Cortex-A78 CPU core. Synopsys design where C5.0 PHY supply chain risk, secure wafer start allocations, substrate capacity, and offset, outsourced assembly and test, slots early, representative companies and tickers. Fables ADM owners, NVIDIA, NVDA, AMD, Qualcomm, QCOM, Apple AAPL, MediaTek, 2454 TW, Broadcom, AVGO, Marvell, MRVL, NXP, NXPI, ST Microelectronics SDM, Infineon, IFXDE, ADRIFNNY, Texas Instruments, TXN, Analog Devices ADI, Microchip MCHP, Onsemi, Renesas, 6723T Cloud-based Vita Compute, Amazon, AMZN, Microsoft MSFT, Alphabet, Google. 2. IP strategy, architecture and system partitioning. What happens with market targets fixed? Architects draft a high-level block diagram. They decide whether the design will be monolithic, chiplet-based, or a mixture of both. For a chiplet approach, a logic die, often on the most advanced node, is paired with a memory or I/O die built on a cheaper node, connected via an interposer or fan-out package. Key decisions. Chiplet versus monolithic. Chiplets reduce reticular size limits and can mix nodes, but add packaging cost and latency. Core and accelerator mix, e.g., 8 high-performance CPU cores, 2 AI matrix units, a DSP, and a security engine. Memory hierarchy on DRAM, HBM3 or DDR5/LPDDR5, and optional on-package cache. External interfaces C5.0/CXL, 112 GB per second SerDes, USB 4, MIPI, Ethernet 800 GB power delivery architecture. Multi-rail, on-chip voltage regulators, DVFS dates, and low-power islands. IP suppliers, CPU, GPU, ARM, C5, private, Imagination, private ASP, Cadenced in Silica, CDNS, CEVA interface, PHYs, Synopsys Designware, SNPS, Rambus RMBS Security, Secure IC, Private, NXP, NXPI. Foundry-specific PDK providers: TSMC, TSM, Samsung, 005930KS, Intel Foundry, INTC, Global Foundries, GFS, UMC, SMIC, 0981HK. 3. Front-end design RTL gates. What happens? Engineers write register transfer level RTL code in Verilog system, Verilog or VHDL. The RTL is simulated functional and timing, and formally verified. Designed for test DFT structures such as scan chains, built-in self-test, BIST, and memory BIST are inserted. Synthesis tools translate RTL into a gettable netlist while meeting the PPA targets. EDA tools: Synopsys VC simulation, design compiler, Fusion compiler, synthesis, prime time, static timing, cadence, Cilium simulation, Jasper Gold, formal, Genus synthesis, Siemens EDA, Questa simulation, Calibre, physical verification. Companies and tickers: Synopsys, SNPS, Cadence, CDNS, Siemens CG80R, Primary ZDE. 4. Physical implementation and sign-off. What happens? The gettable netlist is turned into a manufacturable layout. Steps include floor planning, placement, routing, clock tree synthesis, power grid design, airdrop and electromigration analysis, parasitic extraction, and final static timing sign-off. Physical verification: DRC-LVS ensures the layout matches the schematic and obeys the foundry's design rules. Key EDA: Cadence, Inopus, Placiroute, Voltus, IREM, Tempus, Synopsys, ICC2/Fusion, Placiroute, Star RC extraction, Primetime SA, Siemens Calibre, DRC-LVS Power Thermal, ANSYS, ANSS, Keysight, Keys. Companies and tickers: Cadence, CDNS, Synopsys, SNPS, Siemens CG, ANSYS, ANSS, Keysight, Keys. 5. Tape-out, mask data preparation and photomask production. What happens after sign-off? The design data, GDSI Oasis, is sent to the mask shop. Resolution enhancement techniques, OPC, RET, inverse lithography, are applied to each layer. The corrected data is fractured and written onto reticles using electron beam or laser writers. UV masks require pellicles to protect the pattern from contamination. Mask providers: Photronics, Plab, Toppen, 7911T, Dynapon Printing, 7912T, Hoya 7741T, mask blanks and pellicles. Equipment: ASML, for UV scanners, Nikon, 7731T, and Canon 7751T, for dub tools. 6. Wafer fabrication, Feel and Beal. What happens? The foundry processes bare silicon wafers, typically 200 mm or 300 mm, through hundreds of steps: deposition, lithography, etch, ion implantation, chemical-mechanical planarization CMP, cleaning, and metrology. Front end of line, Feel, builds the transistors. Back end of line, Beal, creates the interconnect layers, often using copper local dielectrics and multiple patterning for advanced nodes. Foundries: TSMC, TSM, Samsung, 005930KS, Intel Foundry, INTC, Global Foundries, GFS, UMC, SMIC, 0981HK. Key equipment suppliers: lithography, ASML, Nikon, 7731T, Canon 7751T. Etch and deposition: Applied Materials AMAT, Lam Research, LRCX, Tokyo Electron, 8035T, ASM International, Azimuth, ADR-ASMIY. Metrology Inspection, CLA, CLAC, Anta Innovation, Anta, Nova, NVMI, Camtex CAMT. Ion Implant, Axelis, ACLS. Thermal Processing, Kokusai Electric, 6525T. Wafer suppliers: Shinetsu Chemical, 4063T, SUMCO, 3436T, Siltronic, WAF-DE. 7. Materials, gases and consumables. What happens? The fab consumes ultra-pure gases, argon, nitrogen, hydrogen, fluorine-based chemistals, photoresist, developers, CMP slurries, and a host of filtration and handling products. Traceability and quality control are critical because a single contaminant can ruin an entire lot. Suppliers: specialty gases, Linda, Lin, Air Liquide, AIPA, Air Products, APD. Photoresists and chemicals, JSR, 4185T, Tokyo Okakojo, 4186T, DuPont, DD, Merck KGA, MRKDE. CMP slurries and FOPs, Entegris, ENTG, Kama Pellicles, Mitsui Chemicals, 4183T, also supplied by Hoya. 8. Yield engineering, process control and DFM. What happens? Inline metrology, overlay, CD, defect density, and statistical process control, SPC, feed data to yield engineers. Failure analysis labs use FIB, SEM, and electrical probing to root cause defects. DESIGN for manufacturability, DFM. Teams work with the foundry to adjust OPC, tighten design rules, or issue steppings, minor mask revisions, to improve yield. Key vendors: CLA, CLAC, Anta, Nova, NVMI, Applied Materials AMAT, Synopsys, SNPS, DFM Tools, Cadence, CDNS, Pattern. 9. Wafer sort, probe and binning. What happens? Automated test equipment, 8. Contacts each die via a probe card. Functional, parametric and speed tests are run. Dies are binned by performance, e.g., high speed, low power, and bad dies are inked or mapped out. Known good die, KGD, maps are essential for multi-D packages. ATOM probe suppliers Teradyne, TER, Advantest, 6857T, Form Factor, Form, Kohu, Kohu. 10. Assembly, packaging and final test. What happens? Good dies are singulated, attached to a substrate, wire bonded or flip-chipped, underfilled, molded, and marked. Advanced packages may involve 2.5D interposers, CoWoS info from TSMC, fan-out wafer-level packaging, FOWLP, or 3D stacking with through-silicon vias, TSVs. Final test, burn-in, functional, and parametric, screens for early-life failures. OSAT's ASE technology, ASX 3711 TW, AMCOR, AMKR, JCET 600584 SS, Powered Etch 6239 TW, Chipland 6147 TW. Substrate and material providers Ajinomoto 2802T for ABF films, Ibiden 4062T, Chico Electric 6967T, Animicron 3037 TW, Nanya PCB 8046 TW, Adines, ATS 6. Test equipment Teradyne, TER, Advantest 6857T, Kohu, Kohu. 11. Logistics to chip customers. What happens? Finished ICs are drip hacked with desiccants, labeled with lot date codes, and shipped to OEMs, ODMs or distributors. Documentation includes certificates of conformance, RoHS declarations, and, for automotive, PPAP, production part approval process records. Distributors Arrow Electronics ARW, Avnet, AVT, WPG Holdings, 3702 TW. Freight and Logistics DHL, DPDHLDE, FedEx FDX, UPS UPS. 12. Board level integration, firmware and system validation. What happens? OEMs or EMS partners place the chip on a PCB together with power management ICs, memory, RF front-ends and sensors. Firmware BIOS is developed, and the board undergoes bring-up, characterization, and validation EVT, DVT, PVT. Regulatory testing, FCC CEUL, and reliability stress, HAS, are performed. For automotive, the chip must meet AEC Q100 and ISO 26262 functional safety requirements. EMS ODM firms Foxconn, 2317 TW, Pegatron, 4938 TW, Quanta, 2382 TW, Compal, 2324 TW, Wistron, 3231 TW, Jabal, JBL, Flex, Test and Measurement Keysight, Keys, and Ritsu, 6754 T, Roden Schwartz, Private. 13. System assembly, software enablement and factory test. What happens? The finished board is integrated into the final product, smartphone, laptop, server, vehicle ECU. Manufacturing lines flash the operating system, calibrate radios, provision security keys, and run end-of-line functional tests. The product is then boxed for retail or enterprise distribution. Representative OEMs Apple AAPL, Samsung, 005930KS, HP, HPQ, Dell, Lenovo, 0992HK, Asus, 2357TW, Sony, 6750AT, Xiaomi 1810HK, Supermicro, SMCI, HPE, Continental, ConDE, Denso, 6902T, Aptiv, APTV. 14. Distribution, after-sales support and field feedback. What happens? Demand planning systems allocate finished goods to regional warehouses, e-commerce platforms and carrier networks. After-sales service captures failure data, which feeds back into the design and process teams for future revisions, e.g., ECOs, stepping revisions, or new process tweaks. Retail and carrier partners Amazon, AMZN, Best Buy BBY, Verizon VZ, AT&T, T-Mobile, TMUS, Logistics DHL, DPDHLDE, FedEx FDX, UPS. 15. Timeline, critical path and feedback loops. Concept to PIA at 6-24 months, depending on complexity and node maturity. Mask build 1-3 weeks. UV mask sets can be longer. Fab cycle 8-16 weeks for a 5nm process. Longer for mature nodes with many metal layers. Assembly and final test 2-6 weeks. System integration 4-12 weeks. Heavily dependent on board design and software bring up. Feedback loops are essential. Wafer sort data drives yield learning, which may trigger minor ECOs or mask steppings. Field failures, e.g., a specific speed bin that fails under certain temperature conditions, can prompt a design revision for the next product generation. 16. Capital expenditure, cost structure and economics. Mask set cost $5, $12 million for a leading-edge node. UV wafer cost $8,000 to $15,000 per 300mm wafer at 5nm. Lower for mature nodes. Test and assembly $30 to $150 per die, depending on package complexity. NRE, non-recurring engineering, EDA licenses, $2, $5 million per year. IP licenses, royalty-based or upfront, prototype boards, and validation labs. A typical high-performance SoC may have a bill of materials BOM split roughly 45% silicon, 30% packaging substrate, 15% test, and 10% logistics. Cost down levers include design shrink, moving from monolithic to chiplet, and negotiating volume wafer start contracts with foundries. 17. Sustainability, environmental and safety considerations. Energy fab utilities consume 100-150 MW. Many foundries now source a portion of power from renewables, e.g., TSMC's 2025 target of 40% renewable electricity. Water, ultra-pure water recycling systems, e.g., Veolia-type plants, reduce consumption by 80%. Chemical management, strict handling of per and polyfluoroalkyl substances PFAS, and other hazardous chemicals, compliance with RoHS. REACH and the EU's Green Semiconductor Initiative. Waste silicon slurries, spent photoresist and mask waste are either recycled, e.g., silicon carbide recovery, or disposed of in certified hazardous waste facilities. 18. Geopolitical, export control and standards landscape. Export controls. The U.S. Entity List, EU dual-use regulation, and Japan's strategic export rules affect shipments of advanced lithography equipment, ASML, and high-performance AI accelerators trade tariffs on semiconductor equipment, e.g., U.S. China tensions can shift sourcing decisions toward known U.S. suppliers, e.g., Tokyo Electron, 8035T, Standards bodies JEDEC for memory, PCI SIG for interconnects, USPIF for USB, IEEE for Ethernet, and ISO 26262 IATF 16949 for automotive safety. Compliance is verified during validation and is a prerequisite for volume production. 19. Summary. The journey from a market-sizing spreadsheet to a consumer holding a sleek smartphone or a data center server is a tightly choreographed dance of dozens of companies, each contributing a specialized piece of the puzzle. It begins with product owners, NVIDIA, AMD, QCOM, AAPL, etc. setting PPAC goals and choosing a foundry node, TSM, 005930KS, INTCIP vendors ARM, SNPS, CDNS, supply reusable blocks, while EDA firms SNPS, CDNS, CG, turn those blocks into silicon-ready layouts. Mask shops, PLAB, 7911T, produce the intricate reticles, and equipment makers, ASML, AMAT, LRCX, enable the fab to pattern billions of transistors. Materials suppliers, LIN, 4063T, ENTG, keep the line running, and yield engineers, CLAC, on to continuously improve defect densities. After wafer sort, TAR, 6857T, and offset assembly, ASX, AMKR, the chips travel through logistics networks, DPDHLDE, FDX to OEMs AAPL, 005930KS, HPQ, who integrate them into finished products, which finally reach retail channels AMZN, BBY and end users. Each step is underpinned by capital-intensive equipment, strict quality systems, IATF 16949, ISO 26262, and an ever-evolving regulatory and geopolitical environment. The entire ecosystem, from cloud-based design farms to advanced packaging substrates, must work in concert to deliver the billions of chips that power today's digital world. Below is a comprehensive, end-to-end overview of how modern semiconductor chips move from planning to shipping. It covers the technical flow and the business mechanics, with representative companies involved at each step and their stock tickers. In practice, many activities proceed in parallel and iterate, but the sequence captures the core life cycle. 1. Market discovery and product definition. Activities: define target markets and use cases, estimate TAM, SAM, SUM, set price margin aspirations, analyze competitors, architectures, process nodes, software stacks, supply strategies, and likely roadmaps. Translate insights into measurable goals for performance, power, area, and cost. PPAC, typical product owners, fabless ADMs, NVIDIA, NVDA, AMD, Qualcomm, QCOM, Apple AAPL, MediaTek, 2454 TW, Broadcom, AVGO, Marvell, MRVL, NXP, NXPI, ST Microelectronics SDM, Infineon, IFXDE, ADR, IFNNY, Texas Instruments, TXN, Analog Devices ADI, Microchip MCHP, onsemi, Renesas, 6723T, cloud compute for data collaboration and modeling, Amazon AWS AMZN, Microsoft Azure MSFT, Google Cloud Google Outcomes, Product Requirements Document PRD, PPAC targets, and initial program plan with budget and milestones. 2. Architecture and IP strategy, activities, decide monolithic die versus chiclet partitioning, e.g., logic on an advanced node, I/O on a mature node, high bandwidth memory on package, choose CPU, GPU, DSP cores, accelerators, interconnect topology NOC, memory hierarchy, and external I/Os, make versus buy for IP and foundation libraries, representative IP and library vendors, ARM CPU, GPU, SoC IP, ARM, Synopsys Designware IP, SNPS, Cadenced in Silica DSP and Interface IP, CDNS, CEVA DSP IP, CEVA, Rambus Memory Des Security IP, RMBS, Foundry PDKs, Foundation and I/O libraries, TSMC, TSM, Samsung Electronics, 005930KS, Intel Foundry, INTC, Global Foundries, GFS, UMC, SMIC, 0981HK, Outcomes, Block Diagrams, Interface Specs, Licensed IP Portfolio, and Co-Design Plan with Foundry and Packaging Partners. 3. Front-End Design RDL to Gates, Activities, Microarchitecture, RDL Coding, Unit System Simulation, Formal Verification, Lint-CDC Checks, Power Modeling, DFT Insertion Scan, MBIST, LBIST, Synthesis to Gate Level Netlists, Early Timing and Power Closure, EDA Providers, Synopsys, SNPS, VCs, Design Compiler, Fusion Compiler, Primetime, Cadence, CDNS, Celium, Jasper Gold, Genus, Siemens EDA under Siemens AG80R, CG, Primary, ZDE, Questa for Simulation Verification, Outcomes, Verified RDL, Synthesized Netlist, Timing Constraints, Test Strategy. 4. Physical Implementation and Sign-Off, Activities, Floor Planning, Place and Route, Clock Tree Synthesis, Power Grid Design, IREM Analysis, Parasitic Extraction, Static Timing Analysis, Physical Verification, DRC-LVS, Eco-Closure, Signal Power Integrity Checks, Thermal Checks, Package Floor Plan Alignment, Tools and Analysis, Cadence, CDNS, Enopus, Voltus, Tempus, Synopsys, SNPS, ICC2/Fusion, Star RC, Primetime SA, Siemens EDA, CG, Caliber, DRC-LVS, ANSYS, ANSS, Red Hawk SC, iSpec, Keysight, Keys, Signal Integrity RF QSIM, Outcomes, Sign-Off Clean Layout, GDS Oasis, Timing IREM Closure, and Tape-Out Package Collateral. 5. Tape-Out, Photomasks, and Lithography Readiness, Activities, Mask Data Prep, Optical Proximity Correction, OPC, Resolution Enhancement Techniques, RET, E-beam mask writing, mask inspection, UV pellicle planning and mask blank selection, alignment with Foundry scanner availability, mask shops and blanks, Photronics, PLAB, Toppen, 7911T, Dynapon Printing DNP, 7912T, Hoya 7741T, for masks and blanks, pellicles from Hoya 7741T, and Mitsui Chemicals 4183T, Lithography Ecosystem, ASML, for UV scanners, Nikon 7731T, and Canon 7751T, for DOV outcomes, full reticle set ready for wafer starts. 6. Wafer fabrication, field to BIL, activities, field, transistor formation, implant, anneal, epitaxy, gate stack, BIL, interconnect layers deposition, lithography, etch, CMP, cleans, inline metrology, defect inspection, SPCAPC for process control, UV at advanced nodes, foundries, TSMC, TSM, Samsung Electronics, 005930KS, Intel Foundry, INTC, Global Foundries, GFS, UMC, SMIC, 0981HK, Memory IDMs, when relevant, Samsung, 005930KS, SK Hynix, 000660KS, Micron, Mu, Western Digital WDC, NANJV, partner Kioxia is private, core equipment suppliers, Applied Materials AMAT, Lam Research, LRCX, Tokyo Electron, 8035T, ASM International, Azumas, ADR, ASMIY, CLA, CLAC, Anta Innovation Anta, Nova, NVMI, Camtaxi AMT for metrology inspection, Axelis, ACLS, for ion implant, Kokusai Electric, 6525T, and Tokyo Electron, 8035T, for thermal processing materials and gases, wafers, Shinetsu Chemical, 4063T, SUMCO, 3436T, Siltronic, WAF-DE, gases, Linda, Lin, Air Liquide, AIPA, Air Products, APD, Photoresist Chemicals, JSR, 4185T, Tokyo Okokogyo Talk, 4186T, DuPont, DD, Merck KGA, MRKDE, Contamination Control CMP FOPS, Entegris, ENTG, Facilities and Utilities, Ultra-Pure Water and Waste Treatment, Vialia, VIPA, Curita, 6370T, HVAC Cleanroom, Dickin, 6367T, Outcomes, processed wafers with multiple die per wafer, meeting parametric specs. 7. Yield engineering and DFM feedback, activities, inline control, overlay, CD uniformity, wafer mapping, defect Pareto analysis, silicon phi using FibSem, correlation of design patterns to defects, design for manufacturability tweaks, mask revisions, steppings, to reduce systematic defects, key vendors, CLA, CLAC, Anta Innovation Anta, Nova, NVMI, Applied Materials AMAT, EDA DFM, Synopsys, SNPS,